In the last section of this module, of this unit and of this module, we'll look at a more sophisticated data structuring technique that I called exhaustive tabulation. It's also known under the slightly unfortunate name for Russians technique. I'll come back to that in a second. And this will be using the 2n bit encoding of binary trees that we've seen in the previous section to finally get the arrangement query problem solved in optimal preprocessing time. It goes back to, maybe not surprisingly, to a paper written by Russians, but it's not even clear. I couldn't dig out if all are Russians. Two are Russian. It was the Soviet Union at the time, and some American authors who were working in this area. I don't know where I couldn't find who was the first who committed the original sin, but it became known as the 4 Russian trick, which is maybe a little derogatory. Maybe we shouldn't call it like that. So instead, I like to call it the method of exhaustive tabulation. It's also much more descriptive. But I wanted to put this here because if you read, okay, slides are gone. If you read about this technique, you will often see it called the 4 Russian trick. So it's useful to know that this is meant. I don't think it's particularly good to call it like that. It's not very helpful and not even historically accurate. Good, there we are. And so what is the exhaustive tabulation trick? To make the confusion perfect, it's also sometimes called bootstrapping, because it feels very, that's maybe not fair to say. Bootstrapping is a technique that you use in combination with this exhaustive tabulation. By bootstrapping, people mean if you pull yourself on your own bootstrap out of the swamp, which in real life doesn't really work, right? There's no, the physics doesn't work out for this. But computer geeks sometimes have a weird sense of humor, so you still call it to boot up a computer. That comes from Bootstrap, because there's a little program that pulls out a bigger program, and that starts the operating system in some way or another at different levels of abstractions. So that's still where it comes from. The idea of bootstrapping, when people use this term, is you somehow use something you already have and pump that up to get something better out of it. What does that have to do with arrangement queries? We know this sparse table solution, which again, n log n query time, pre-processing time and space, but constant query time. So that part we were happy with. It's just not quite linear. We would like something with linear pre-processing time. If we somehow thin out our input, don't use all the elements, but just every log nth element, then we can reduce the number of elements to m, which is then n divided log n. And if you insert that, m log m, insert the definition, you get linear. So the bootstrapping part is we use the solution, the sparse table one, which is not fancy. We've seen how this works. We use that as a black box, but on a smaller input. We first have to throw out almost all the numbers. Just a 1 over log n fraction remains. But on these numbers, we can use the existing technique and we get the optimal pre-processing time. So here's an example how this works. And I want to point out that the size of these blocks is chosen so that the rest works out. For now, you could have chosen any constant in front of the log n. But it will become important that these blocks are not too big on the next slide. Be it as it may, we break our array into blocks. And the blocks have roughly log n divided by 4 elements. Each of these little blocks has a minimum somewhere, or a leftmost occurrence of a minimum. And these minima we promote to a different array, B. And that's a much smaller array. It has only m numbers because we have blocks 1 up to m, or blocks 0 up to m minus 1. Shall we give those names? So this is the block with ID 0, block with ID 1, and so on. So we would end with block m minus 1. And then the ith entry in this blue array is just the index of the minimum inside the ith block. So you just store the result of the range min query if you query for the block. So far, so good. If we use the sparse table data structure for this small array B, the overall space is order n for the preprocessing, and query time is constant. So we can solve range minimum queries on this array B. That's great, but it's not what we originally wanted, so it's not so clear yet how to make use of that. But we can puzzle together a general query out of different pieces now. So again, the red range is our actual query, and it can cover any range. In particular, we have no guarantee that the user of this data structure respects our block boundaries. If the query was exactly from block I to block j, we could just reduce it to the B array. But in general, this is not working, so we could have the query like this. In this case, we're lucky because the block minimum is actually included in the red range, but we don't know if that's true. And if it's not true, we don't know where the next smaller element is. But we can always take our query and split it into 3 queries. And some of these can be empty. There will be a range in the middle that is only on block boundaries, only whole blocks. So the blue part is always from a certain block to the end of another block. And we have 2 green queries, which are not respecting the block boundaries, but they're always inside a single block. Okay? If I know the minimum from the blue range and the 2 green ranges, it takes me 2 more comparisons to find the overall minimum. Right? That's easy. You just take the first compared to the middle one. If it's smaller, you keep the minimum in your hand compared to the last one. That's the usual way. The important part is constant time to find the minimum of the red range if we know the minima of the blue and the 2 green ranges. You can spell this out more carefully in this formula. The range min query for the red range actually asks for the index k, where the array is minimal, and leftmost of these. And this range k is just 3 numbers now. The minimum from the green part, the minimum from the blue part, the minimum from the other green part. And you can work out the blue part is an offset of you ask the B array for the minimum in this range. Why do I have to add the B times RMQ? That's the block size. Okay, that's the case before this. So if this was the minimum in the blue part, then this here would give you the offset inside the block. And this one would give you the number of blocks left of it. So you have to puzzle together the entire offset as the sum of how many blocks are left of this and where in this block that contains the minimum is the minimum. And that's something you can store in this array. For the green ranges, it's a little easier, and here you can restrict it. You could write RMQ with respect to the whole array A, but you can restrict it to just one block because we know it's inside a single block. So at the end, what I said already, we have 3 values to check, and that's easy to do. Moreover, we know how to deal with the blue range. The blue minimum only needs RMQ computations on this B array. And we know that we can use the sparse table data structure for that. What's left is these green ranges. We know they're all small. They only ask for the small ranges up to log n over 4 elements. But we don't have a solution for those yet. So what's left is these intra-block queries, the queries that are contained entirely inside one block. We want overall the same time that we got for the blue range, so linear preprocessing, constant query time. But we have many, many blocks. The number of blocks is n over log n. So we somehow can only spend log n preprocessing time per block. And that is linear. So it means we would already need an RMQ data structure with linear preprocessing to build the data structure that has linear preprocessing. That's a chicken egg problem. And that's where the second part of bootstrapping comes into the game. If you look at one such block, it only contains log n over 4 it contains log n over 4 numbers. And we've seen that there's not so many Cartesian trees. If I have B elements, there's only roughly 4 to the n different Cartesian trees. There's a few less, but this is an upper bound. So we can use at most 2B bits to encode any Cartesian tree inside the little block. So all the possible arrangement queries inside a block, the answers can only be 1 out of 4 to the B different equivalence classes. And at least information theoretically, if we only want to specify what's the right answer without regards to how to find it, it's enough to store 2B bits for each block. And if you do the math here, this 4 to the B with our choice of B works out to be square root of n. That's not that big. So we have a lot of different blocks, n divided log n, that's almost n. But they come from just square root n different types. So almost all are kind of duplicates. They look exactly the same through the arrangement query classes. And so we can try to encode them in a more efficient way. And that's where the exhaustive tabulation comes into the game. So we know we have many blocks, but they all look like just a small number of different blocks. So we store for all the different possible options how they can look like explicitly what the answers are. And we only store for each block which type it is. So we will store 2B bits for each block to encode the Cartesian tree in a way that is not really useful to extract the answers, but we don't care, because we also enumerate all possible Cartesian trees and all possible arrangement queries with their answers. I'll show a table on the next slide that makes this a bit more concrete. And we just pre-compute all possible Cartesian trees. And that way we get around this problem that we have these many blocks that we can't really spend time on by reducing it to the much smaller set. So this is the invention behind the 4 Russian trick, the exhaustive tabulation. You have many little blocks, but they come from a small set of different blocks. This representation of the Cartesian tree can be computed in linear time, exactly using this algorithm that I explained to you. The traversal is linear, and the type of each node to find is easy to do in constant time. And so what we do is we compute one giant lookup table. And let's fill out just for our small example that we had earlier. So this type of tree, that's the one that we encoded in binary. So we did our traversal. This one has both children, so the code is 1, 1. Then we go to this node that only has left child, 1, 0, and 2 leaves. Okay. So I would put an entry for this block type. And every combination of I and j. In my case, this is just 4 elements. Right? So this would correspond to a fairly small array of 4 different elements. And now I can ask, what are all the possible arrangement queries I could ask for this tree? For example, I could ask from 0 to 3, the entire range. What has to be the minimum in this case? Does anyone remember and is willing to puzzle the pieces together? Remember, RMQ on the tree translates to going to the nodes of the same in-order index and jumping to the lowest common ancestor. So 0, 3 are these nodes. Lowest common ancestor is the root, which has index 2. So I would put a 2 in here. Okay, that's how it goes. And you would fill in all the other combinations, right? There's not a ton in this small example, so we could actually go through these. 0, 1, the lowest common ancestor is 1. 0, 2, we get 2. 1, 2, we get 2. 2, 3, we get 2. You see a lot of 2s here in this small example because that's the root. If the tree gets a bit bigger, then it's a little less boring. And you would copy this in each cell. Should have copied more than one, huh? I'm missing the 1, 3, but never mind. We could smuggle one more in. Same answer. So this is the idea behind this. If our block size was 4, there would be these 6 rows for this one choice for the Cartesian tree. There's a lot of other choices to have a tree over 4 nodes, right? So this table would go on for a while. But it wouldn't go on for too long because there's only root n different trees. And if our array has length n, spending root n extra space is actually a fairly small amount. So we have square root n different block types. We have roughly b squared combinations for I and j. It's a few less because they're in order. So we have square root n times log squared n rows. Each row, if you do it naively, can be computed in log n time. So if you multiply that all together, you're still far below linear. So the computation of this seemingly huge exhaustive table is actually a tiny fraction of the overall time. It's the least expensive bit, even though it seems to take a while, but it's compared to the big array, it's nothing. And so I should probably have said this before. If you go back to the green queries, the way to solve the green queries is to look up in a table what's the type of this green block, and to compute the 2 ranges that you're interested in, the I and j. And then there is one big array that has as one index the block type. So you just use that type as a number and jump into the right row and use I and j as the next indices. So it's some multi-dimensional array. and the result is just stored there. So these green queries are very simple. It's just a bunch of array lookups, table lookups. Should probably say this uses that we are working on the word RAM machine with log n bit words. That's from far back. I told you about these machine models in, was it unit 1 or 2? 1, I guess. So this depends a bit on your machine model, whether this counts as constant time array lookups. But on all computers that we have, you can do array lookups like this. So I think it's fair game to say it's constant time. So you can puzzle all this together. You get an arrangement query data structure that has linear pre-processing time, constant query time, and that's the best we can hope for. You can plug this into the longest common extension data structure from Unit 6. So that closes the last magic black box we didn't dare look into at the time. With a little bit of a stretch into the world of data structures, you can fill this black box as well. I called it a bit complicated. You'll be my judge. This is also something that people still look at a bit. You can ask the question if you can reduce the space further. And a second nifty bit is you can build data structures that don't need the array at query time. So I can give you the array for pre-processing and then take it away from you. So you can only answer the arrangement queries then and don't even have the knowledge what is in the array.